Victor and I are just going to be going back over the same paper from last week. We found some things that weren't exactly covered properly, and then also some of the results that were drawn from the paper, we aren't exactly sure about that, so we also wanted to talk a little bit about that as well. So I guess we'll just take it from the top again and for a refresher, because I know there was a lot of information last time. So we can just go back over what quantum walks are. And okay, so we know that from last time, random walks, they're just like these stochastic processes. You can, one example of that is like if you start on a number line, you can start at 0, let's say, and you can flip a coin to determine, are you going to the left or you're going to the right? That's one possibility for a random walk. They have, as we discussed last time, many real-world applications in these types of fields, and it can lead to some interesting results. And it's nice because it doesn't require too much framework to define them. So you can define them relatively easily, but you can get something more complex out of it in terms of its behavior. So two major implementation drawbacks that the paper talks about is that there's a large walking space that's demanded, and the walking space being where the thing that's traversing the quantum system that's related to this quantum walk. And then we have this problem of implementing global unitaries is not practical. So me and Victor were talking a little bit about this. I'm not sure if you came up with something new in the time that we talked, but we're trying to understand like how exactly the unitaries for these quantum walks are global. I'm not sure if you want to add something here or not, Victor.
Yeah, so like I didn't figure out anything new, but I do want to restate. So the purpose of this paper is essentially we're trying to use quantum cellular automata to simulate quantum random walk, simply because the author, they made the statement that the quantum cellular automata has local unitaries instead of global unitaries, and that's going to be the source of advantage in that kind of simulation.
I have a quick question, if it's okay. So what's exactly the difference between quantum random walk and then normal random walk?
So I think the quantum random walk, the thing, like, so if you have a random walk, right, and you flip a coin, then you deterministically know that, okay, I'm either going, if going back to that number line example, I know for sure I'm either going to the left or the right. In a quantum random walk, you get some sort of superposition of going to either the left or the right. So let's say you're trying to look for like a particular outcome. Let's say this is a graph, right? And you're trying to traverse this graph. And let's say we're searching for a particular node on this graph. So if we were to do this deterministically, then we can flip a real coin, or like a classical, a coin with classical probability. And every time we flip it, we know how to traverse that graph. But every time we traverse the graph, we're going to exactly one place, right? It's not like a superposition of different movements.
I see. Okay.
In a quantum walk, you can define you can define the states as like the different different movements that you can make from a given node, and taking the superposition of all those possible movements, you can essentially traverse the graph much faster. So if you're looking for a particular node on the graph, that process would take place much faster, because technically you're traversing all the possible nodes of the graph, or like from a given node, you're able to traverse all the possible paths at once. So you would be able to find your marked node quicker. So that's like the main difference.
Okay, that makes sense. Cool.
All right. So yeah, those are the two major implementation drawbacks with quantum walks. So now let's talk about the cellular automata. As Victor said, that the goal of this paper is trying to take these quantum walks and address the drawbacks that they have, which is they have too large of a walking space, and also we're having to deal with these global unitaries, or that's what the paper is positing, that implementing a global unitary is a pretty compute intensive process, and ideally, that makes up implementing these types of quantum walks less practical given the state of quantum computers right now. So then what this paper is saying is that let's try and take this form of the quantum walk, but represent it in a form that's not as compute intensive. So what they're proposing is using a quantum cellular automata. So I'll just talk a little bit about what the classical counterpart is. So the classic example is Conway's Game of Life, which looks like this. So if you're looking at this more generally, basically your cellular automata would consist of some d-dimensional grid of cells, which is referred to as a lattice. And then every cell in this lattice can take on one of finitely many states. So there can be k such states, and we can, at any given time step, any one of these cells can take on one of these states. And we can define a way of evolving this lattice structure over time using a notion of a neighborhood. So if you were to consider every cell in this lattice, you would like whatever the cellular automata's goal or usage is, you can define a neighborhood, which is typically just all the adjacent cells to a particular cell, and define some sort of evolution rule based on that. So in Conway's Game of Life, every cell is either alive or dead, and that's sort of representing a metaphor for life in that way. So given the current state of a cell, if you look at the cells adjacent to a given cell, then that would tell you in the next time step what's that cell going to look like. So for example, if I were to just pick this cell over here, I don't know if you can see that, but there's three I guess alive cells next to it and one dead cell in the center. So let's say that our rule set is saying that, okay, if you have at least two alive cells next to you, then you will be alive in the next time step. So in the next time step, the whole state of the lattice will evolve, and then this particular square will then be alive. So that's sort of the idea behind the cellular automata. Obviously, this paper is trying to characterize the cellular automata quantumly. So how would we do that? Is there anything that you wanted to add, Victor? Okay. So just to reiterate, there's two main steps in how we're actually progressing the state of the cellular automata. So we want to know, based on whatever neighborhood we've determined, we want to know what the states of those neighboring cells are and use that to update our cell. So these are the two steps. We retrieve the states of the neighboring cells, and then we alter our states of our current cells accordingly. And so now we want to be able to mimic this behavior in our quantum cellular automata. So how do we do that? Well, first, there's some challenges that we have to address with that. So the first thing is that we can't clone quantum states, and that's by the no cloning theorem. And also, the more important part is that these classical cellular automata evolution methods are typically not reversible. And that's a big problem if we're trying to implement this in a quantum computer, because as we know, if we're dealing with unitaries, these unitaries are inherently designed to be reversible. And since that's not really that may not be the case with these classical cellular automatas, it's translating them from the classical realm to the quantum realm is not so straightforward. So how are we going to work around these issues? So the paper proposes defining this sort of obscure quantum cellular automata, which they define as a partitioned unitary quantum cellular automata. So recall that we have a cellular in our classical definition. We have a d-dimensional grid which defines our lattice structure. Then we have some sort of neighborhood defined on every cell in this lattice. And then we have some sort of evolution rule that will tell us that, okay, these are how the node, or these are how the cells in our lattice is going to evolve over time based on some sort of locally defined rule set. So in this definition of the, I'm just going to refer to it as the PUQCA. They borrow from this Margolis block scheme, which basically just defines some neighborhood scheme. And then they define a way to implement unitaries that would then, act on these neighborhoods. And the whole idea is that with the classical cellular automata, we have the issue of that the evolution methods aren't always reversible. So obviously, to make them reversible, we're going to have to use some sort of unitaries there. So it's also called a partitioned unitary QCA. We got the unitary part out of the way. So why do they call it a partitioned QCA? So basically, the idea is that suppose we have this d-dimensional lattice. They're supposing that, let's say that we split every cell in this lattice into we split it further into subcells. And basically what they're saying is that by splitting it up into subcells, we can get some finer characteristics of our PUQCA. And the idea being is that, we can gauge the interaction between neighboring cells at a finer level. So we can consider neighboring subcells across different cells. And then we can also consider subcells within a given cell. So, that gives us a better understanding, or, a more in-depth understanding of how this system can evolve over time. Okay, so now I'm gonna slow down a little bit and give you guys the formal mathematical definition of this PUQCA. So the paper defines it using a 5-tuple. So there's 5 main components that go into define one of these quantum cellular automatas. So as I said before, we start with this d-dimensional grid / lattice. And since we want to keep track of every single one of these cells, we index it according to these set of integers. Also later on, you'll see that they'll switch over from a lattice representation for the cellular automata to a graph representation. And the reason is that, past 3 dimensions, it becomes pretty difficult to visualize what like a 4D or a 5D grid or like a lattice looks like. So it becomes much easier to define this quantum cellular automata in terms of a graph where every node can have, D connections. And that would be an analogous structure to our lattice, when we're defining our neighborhood. So you'll see that I'll eventually start talking about a graph instead of a lattice explicitly. And as I said before, we have to define some sort of neighborhood scheme, and the neighborhood scheme is important to tell us, like, every evolution, how is the state of the node we're currently looking at, how is that going to change based on our neighborhood. So we define that as some sort of a local, it's some sort of locally defined set of subcells. And we're seeing already that I keep mentioning this idea of locality. And that's important because we're trying to address the drawback from the quantum walk, which was that we're having to apply, or so the paper says, we're having to apply these global unitaries. And in this case, in translating to the quantum cellular automata, we no longer have to do that because we've defined this neighborhood scheme, which is defined locally on each of the subcells. So therefore, as you'll see later, we'll be able to define local unitaries that will act on these neighboring subcells. Then we define a set of orthogonal basis states. Obviously, since we're working in this quantum realm, we have to characterize the space that like the Hilbert space that we're working with. And that's defined pretty intuitively, I think. So the total space, so every cell has a certain Hilbert space associated with it. And then the total space is just the tensor product across all those Hilbert spaces for each of the cells. All right, so now comes another important part, is this idea of tilings. So recall that, we partitioned all of the cells into, we partitioned all the cells in our lattice structure into a number of subcells. And as I said before, that's to characterize some sort of, get some sort of finer characteristics of our QCA. So now that we have these subcells, right, we want to be able to gauge not only interactions within a cell, but we also want to figure out interactions between neighboring cells. And the way we do that is by defining these set of tilings. So you can think of a tiling as a partition of the entire lattice of a cellular automata. So if you're to take the union of all of these lattices, or if you're to take the union of all the tiles in a given tiling, you would just get back the entire lattice. So we can define different partitions on this set of subcells, and we can use that as a way of defining unitaries. And that's where this idea of the local unitaries comes into play. So you'll see that every tiling, or rather every tile has a unitary, every tiling has a given unitary that's associated with it. So those two things will go hand in hand, and that's where our definition for this local unitary comes in. So as you see, we have these finite set of tilings, TIs, which are defined on, each tile contains only subcells of neighboring cells. That's based on the neighborhood scheme. And then we have a set of local unitaries that you see we have as many local unitaries as we do tilings. So we, for every tiling, there's a local unitary that we would apply to that tiling. And that's basically how we're going to evolve the state of the quantum cellular automata. Okay, so just to give a sort of visualization of what this would look like, let's consider a 1D lattice structure. So we can have this lattice structure which has a bunch of cells, and we can divide each of these cells into two subcells. So from there, we can define our neighborhood structure that it's considering a given subcell. We can say that the neighborhood is that cell, the cell to the left of it, and then the cell to the right of it. Which seems pretty intuitive because those are the cells that are most adjacent. Next, we have to define the tilings. So we see that there's two ways that we can do this. We can either pair subcells within the same cell. So if we have this cell here, we can consider tilings where it only considers pairs that are within the same cell. So like this would be one tile, this would be another tile, and this would be another tile. And as you see here, that would be corresponding to the unitary W0. Or we could define a tiling that's across cells or across neighboring cells. So this is a tile, this is a tile, and then that keeps going on. And we see that we're applying the unitaries W1 on these particular tilings. So so again, as I was saying, you can define the W0s on pairs within the same subcell, and then W1 on pairs across cells. And we can define the spaces for the, we can define the spaces of the mappings accordingly. So here we know that we're indexing each of the cells by some I. So we see that we're dealing with subcells within the same cell here. And also I forgot to note that we're also going to have to naturally give an indexing scheme to our subcells as well. So here we're indexing the 0th subcell within a cell is 0. First one is 1. And here we have, we're mapping the ith cell, the tensor product of the ith cell, or the subcell of the ith cell, 0th subcell of the ith cell with the first subcell of the ith cell. And then here we're mapping across neighboring cells, so I and I plus 1. And then finally, we would define this transition function. So this basically takes all of our unitaries that we've defined and in a ordered manner applies these unitaries to the set of tilings that we've defined in this one after another. So first we would apply all these W0s on the first tiling that we defined, and then we would apply all these W1s on the second tiling that we defined. And the first tiling being all the subcells are within a single cell, and then W1s will be acting on the tiling where the subcells are across different cells. So then more generally, if we're not considering a one-dimensional example here, we can define a very generalized form of this transition function where let's say we have in this case we have however many tilings. Then for each ith tiling, we can apply them one after another across all the subcells. So that's basically how we'd define the transition function for a generalized d-dimensional PUQCA. Does anyone have any questions so far, or anything? Is there anything you want to add, Victor?
Do you guys have any questions, Andrew and Ian?
Yeah, I had a question about the cellular automata.
Right. Yeah.
So I guess what exactly do the tilings achieve? Is that like the transition function between like two neighboring states?
So the tiling, so as I was saying before, with like if we're just considering a classical cellular automata, we need a way of getting the states of our neighboring cells and using that as a way to evolve the state of our cellular automata. So to adapt that for a quantum cellular automata, what this paper is basically suggesting is that for every cell in our cellular automata, we define we split each of those cells into subcells. And then on those subcells, we define these tilings. So it's a way of gathering information about the neighborhood so that we can then evolve the state accordingly. So applying these unitaries is essentially doing the evolution of the states of the subcells.
Okay, so this is kind of like a local search or like simulated or like classical simulated annealing. Or I guess you're just like, or maybe like a greedy algorithm where you're just like looking for like the best local option.
I don't think it's optimizing.
Yeah, I don't know if there's any optimization.
Yeah.
Oh, because it's randomized, right?
No, it's the unitaries are actually predefined. So as the rules of any classical cellular automata, we're assuming that the unitaries are known in advance. So they're evolving with respect to this fixed unitary, but they can be in a superposition state. That's the difference between the quantum cellular automata and the classical cellular automata.
Yeah, so basically we're using these unitaries to evolve the state, but there's no classical algorithm that's used to like fine tune the parameters of those unitaries to get there. Yeah, there's like no optimization taking place in that sense. But what you're saying about the search, yeah, we could definitely use this as a method for searching for a particular marked thing.
I see. Okay. Just to like clarify in the unitary, does it like evolve? Because I know like it evolves by like changing the amplitudes of whatever basis you're in.
Mm-hmm.
I was wondering like what the difference between something like if there is any difference or like what the difference was between that and like something like I think like a state transition matrix is what it's called. Not really familiar, but it sounds kind of like similar, but I don't know.
Yeah, so like if you had a stochastic matrix or something that's defining.
Yeah. Mm-hmm.
I think the concept is similar in a way that like if you have some state or like some graph and you can define like transitions on that graph using a transition matrix.
Right. Mm-hmm.
I think they're analogous, but I guess that the way that it's actually working in the cellular automata is a bit different. Like the idea is the same though. I'd say like the underlying concept behind like a transition matrix and how we're locally applying these unitaries is about the same.
Okay, I see. That makes sense.
All right. If there's no more questions, then I'll just continue. Okay. So there's the transition function. As I said before, we need to have an indexing scheme for our subcells as well, just to keep track of every object of our cellular automata. Okay, so as I said before, it becomes more convenient to represent these cellular automatas as graphs um, rather than actual lattice. For 2D, it would be fine to represent it as a lattice, but I think it's very nice to see what the different tilings look like when we're looking at a graph, especially since for a single node, we can have many neighbors to represent a higher dimensional lattice, whereas if you're doing an actual block style lattice, that would be very difficult to visualize for a person. So we switch over to this 2D 2D model for the quantum cellular automata and the graph model. And then that's where you start to just see the parallels between a quantum walk and a quantum cellular automata, because a quantum walk is also dealing with the graph structure. But in the case of the cellular automata, we're using the graph structure in a little bit of a different way. So as you see here, we define a set of tilings. So in this case, we have 4 subcells for every cell, and we define one tiling where we consider tiling that only considers the subcells within a certain cell, and then we define a second tiling that considers subcells across different cells. So that's how they've color coded it between the red and the blue. Okay, so the paper talks about 2 specific translations that they're interested in. They first mentioned this coined quantum walk and translating that over to a quantum cellular automata. They also talk about this like staggered walk with Hamiltonians. I'm not going to go into that right now because it's pretty complex, and I think this will serve as a sufficient example to help you guys get an idea of how to do the translation. So just to recap what I've gone over so far, I first defined like what the classical and quantum counterparts for the quantum walk are, what the classical and quantum counterparts are for the cellular automata. Then we talked about the particular approach that this paper decided to take with the quantum cellular automata and how they thought it would be best fit in order to translate these quantum walks over to these PUQCAs. And you'll see that the translation part of it actually is pretty intuitive in terms of how it's done. So yeah, so let me start going over what a coined quantum walk is. So at the beginning, I briefly mentioned this idea of a coined or random walk. I didn't say coined, but I gave this example of, let's say you're a walker and you're standing on the number line and you flip a coin, and that coin tells you whether to go to the left or the right on the number line. So we are adapting that idea for this quantum walk where our coin, rather than deterministically telling us to either go to the left or to the right, it puts us into some sort of superposition of going either left or right. So that just sort of gives you an idea of how a coined quantum walk is defined. So we start with this graph G, which has vertices V and edges E. And the quantum state for position and traversable direction is defined as the first element of this state is a ordered pair IJ, and that basically determines the edge that we're concerned with in terms of a direction of travel. And then I represents the current vertex that we're on. So if we have some graph and we're looking at some vertex I in this graph, and there's another vertex J that's connected to I with an edge, then we would represent this state as one of the possible directions that the walker could move to. So if we were to consider all possible J's, that would give us all the edges or all the vertices that are connected to I via an edge or via a single edge. So that's how we define the quantum states for the coined quantum walk. Then, as I said before, defining the graph neighborhood is pretty easy since in terms of the cellular automata, we were looking at cells that are subcells that were immediately adjacent to a given cell that we were interested in. Here we define it similarly in the sense that for a given vertex, we consider all the cells, for a given vertex, we consider all the vertices J that are connected to I via a single edge. and that's how we define the neighborhood. Similarly here, we define the associated Hilbert space. Another thing that me and Victor were a little bit confused about was previously when we were defining the overall Hilbert space for the cellular automata, we saw that they were taking the tensor product across all the cells, but here they're taking the direct a direct sum instead. So I don't remember if we ended up hashing out exactly why that was. I might have forgotten there.
So I think what they're trying to argue is that if we look at the coin quantum walk and their graph structure, each of the vertex has their own space that is not really interacting with other vertices. So so when we are essentially conglomerating them into the entire space, they're actually independent of each other. And that's why so essentially they're not in a superposition with each other. So that's why we're using the direct sum this time, which, when direct sum acting on a space, it's going to be essentially taking the union of them without, entangling them together. But in the case of quantum cellular automata, in that case, our qubit is a subcells. And since they're interacting with each other, we have to take into account of their superposition, which requires us to use the tensor product.
Right. So now we have to define the necessary operators. So this is basically how we would get the walker to walk or traverse the graph. So since we're dealing with coin quantum walks, we define this notion of a coin operator, which is sort of a quantum version of the class of coin that I was defining for our number line example. So we define a coin operator, which basically tells us it gives us a superposition of possible directions that we can travel. Then there's a generalized shift operator, which actually is doing the operation of going from one vertex to another. And then we have the flip-flop operator, which I'm honestly still a little bit confused about what it's supposed to do.
So flip-flop operator, essentially, if we look at the state, right? Each of the state vector here essentially means the option you have at vertex I, right? And if we look at the flip operator's definition, this is saying that, okay, our current state is we are on vertex I, and the direction we're facing is towards J, okay? And when we apply the flip-flop operator, we're actually going to take that edge going from I to J, so we're not at J, right? But which direction are we facing at J? The flip-flop operator is essentially constraining us so that when we got to J, we are facing back towards where we came from, which is I.
And yeah, they didn't really give much intuition as to why they, in the paper, why they chose that particular operator, but because I don't really see how it would matter, because after you shift once, you would still be connected to the edge you were at before. So
yeah, it would matter because, so say that you're at state I, right? Say that you're at vertex I, and you have this probability distribution. You have different weights on each of the option you're going to take, right? And if we pick any permutation, that's going to affect how our weights are distributed on vertex J, right? Because if say that it was originally like 1/3 on IJI, then you're going to have a 1/3 on IJJ if this is what you pick, right?
Right.
But if you pick another permutation, that 1/3 is going to go towards somebody else. So that's going to have an effect on the type of permutation function you pick is going to have an effect on the final state you get.
Right.
And they are picking the flip-flop operator here. So they're going to actually fix that later. Can you go click one more? I think there's a, yeah, so they're going to fix that later. Yeah. So this is what they're doing, right? So at vertex I, you're going to flip a coin, right? And what that does is essentially redistributing the probability weights on your current state. Okay, so now you have an entirely different, essentially, distribution of which direction you can go. Okay, And then what you do is you apply the flip-flop operator. So you actually commit to each of the direction.
Right.
Okay. So essentially, so think about this. If at state I, after the coin flip, you have 1/3 chance to go towards the left and 2/3 chance to go towards right. Right. And then after SI, you're gonna 1/3 of you is gonna be at I-1, and 2/3 of you is gonna be at I+1, right? And you're gonna be pointing towards I because that's what flip operator did, right? It points to where you came from. But that's not always, that doesn't have to be true because, like I argued before, this type of permutation might not be the permutation you actually wanted, right? Maybe you wanted that so that when you go from I to I-1, the 1/3 of you actually points to, key points towards the left instead of pointing back to I. And the 2/3 of you might be pointing to the right instead of pointing back to I, right? So that's why we have this X, which is, in this case, it's going to be a swap operator. But in a more general case, it's going to be essentially another permutation operator or reconfiguration operator that is applied when you actually got to your target vertex so that you reconfigure the probability weights in that target vertex. So
so just to reiterate, sorry, go ahead.
Yeah, it's a bit dense, like how they're defining it. But there are two ways that you can do this, right? The one way is to use a generalized shift operator that we can look at here, right? So like the generalized shift operator, you essentially you take that reconfiguration directly when you are committing the change, right? Because the S pi ij, you directly map to some permutated I, j, right? But the flip-flop operator, which is a special case of the generalized shift operator, doesn't take into account that you have so many different pi I you can choose from, which means that we have to take that into account and reconfigure that using the last operator.
So just to clarify a little bit, Victor is mentioning this permutation. So basically, we're permuting on the graph neighborhood for a given node in the graph, and we characterize this with this X operator. And the X operator here in this paper is defined as a direct sum across swap gates, basically. So for however big your graph neighborhood is, you would take a direct sum with the swap with itself that many times. And basically, if you think about it, a permutation is just comprised of a bunch of transpositions or flipping the position of two elements of, in this case, the graph neighborhood. So we can basically characterize, flipping two elements using a swap, and that's a pretty intuitive way of doing it. So then, if we were to define the overall evolution of our Walker state, we would first have the coin operator, which tells us like the possible directions we can move to. And their related probabilities. Then we have this flip-flop, which, as Victor said, commits to a direction of movement. And then we are applying a permutation, which is this X, basically.
Yeah. So okay, let me try again to make this clear, right? So say this is you, right? I'm not sure if I already made it clear. Please tell me. So
go ahead.
So this is you at this like vertex, right? And say that you're trying to go this direction. If you use the generalized shift operator, right? When it's transitioning, it's already gonna have the direction fixed. When you and then when you arrive at the target vertex, it's gonna be you're good. You don't have to do anything, right? Because the state is already permuted as your desire by your desire during the transition. Okay, so the permutation happened during transition, during your walk.
Right.
But if you don't want to do that, you can use a flip-flop operator and another reconfiguration operator, which means that so this is your state, and then so now you're vertex J, which is your target vertex, right? That's after you applied the flip-flop operator, so you're pointing back to where you came from, and then you apply the X, whatever reconfiguration operator you want, to actually tweak this into maybe this is the direction that you want. You got it? So if you use a generalized operator, this is going to happen during transition, okay? But if you use the flip-flop operator with the X, this is going to happen. So you go there, turn this, and the X is going to, put that into the right direction that you want. I hope that makes sense. That's the best way that I can visualize this for you guys.
So if I'm getting it right, this overall evolution can be replaced by x times the transition operator instead of the si times coin. Is that the case?
So the coin operator is going to act on vertex I, right? The coin operator is going to act on vertex I, and si is going to act across vertex I and j, right? Because that's a transition. And then x finally is going to act on vertex j. So coin operator have to, coin operator essentially what it does is it makes a decision for you. Like it's giving you a list of options, right? Like you are a random walker, coin operator gives you a list of options. And then si gives you the power to commit to all of these actions. Okay. And the final reconfiguration matrix makes sure, at the end of your walk, you're pointing in the direction that you want. And the direction that you want is defined by the algorithm designer. We don't talk about it here. And in many cases, the direction that you want in classical random walk is keep the same direction where you came from. So if you're going right, the next direction you're pointing is still right by default. So it's based on your personal preference. But the X is there just to make sure that you have that level of expressiveness so that you can point in the right direction.
Oh, I have a kind of silly question. Is this a 2D scheme or 1D scheme?
This is generalized. Well, I guess there's no for the coin quantum or like a quantum walk, there isn't really a notion of dimensionality like that since we're just traversing a graph. That notion of dimensionality becomes important when we're trying to translate this graph structure into the structure of the PUQCA.
Okay, got it.
So yeah, so to give a quick example, so if we're talking about if you're talking about like a two, each vertex only has two edges. In that case, right, that vertex space is going to be essentially a qubit, right? That vertex space is going to be two-dimensional because it has two options, right? And in that case, the coin operator is going to be acting on a 2x2. It's going to be a 2x2 operator. And the SI is going to be a 2x2, and X is going to be a 2x2 because they're all acting, on a two-dimensional space.
Okay, so hopefully this description gives you guys an idea of what we're dealing with the coin quantum walk. I know this last part with the operators is a little bit heavy, but I think Victor did a pretty good job breaking that down. So yeah, now we get into trying to translate this into the QCA. So this is the whole, this is the crux of the paper, is trying to take this quantum walk, this coin quantum walk in this example, and translating it to a PUQCA. So how do we do that? So we have to go back and recall that we defined our PUQCA using a 5-tuple. And in our 5-tuple, we had started with our lattice structure. So what's nice here is that our graph already determines what our lattice is looking like. So the number of vertices determines the number of cells. And then recall that this cellular automata is partitioned. So that means that every single cell has D subcells. And how are we defining that? Basically, every that's determined by, so if we define a D regular graph for our quantum walk, then that means that we would have D subcells. And when I say D regular graph, I mean that every vertex has D vertices that are connected to it, or D edges coming from it. So basically, if we define a D regular graph for our coin quantum walk, then our every cell in our PUQCA would have D subcells. Okay. Then now we define our neighborhood scheme, which we just take the graph neighborhood, which we defined as every vertex that's connected to I via a single edge, and we just add the vertex I to it. So it's essentially the same neighborhood structure. Then to define this state for the automaton, we define this transition, or like this mapping between the quantum walk states, the automata state. So given that we have some sort of state iji, where ij is the ordered pair denoting an edge, and then I is the vertex that we're currently on, we define the automata state making use of the indexings of the cells and the subcells. So remember that we defined an indexing on the subcell or for the cells, and we also defined an indexing on the subcells. So we can see here that on the left, we have our coin quantum walk state, and on the right, we have our automata state. So here we're concerned with the ith cell because in our coin quantum walk state, we are on the ith vertex. And then to represent this edge connection, we're sort of like singly exciting this one jth subcell in our set of subcells for a given cell. So we're in the ith cell, and we've excited this jth subcell, which is then how we relate to the quantum walk state. Okay, so this is the most important part now, is how do we take this idea of the three operators that we defined, the coin operator, the generalized shift operator, and the flip-flop operator? How do we translate this into the world of a quantum cellular automata? So remember the last two things, the last two elements of our tuple. Okay, so far we've defined L, which is our lattice structure, N, which is our neighborhood scheme, and then a way to represent the quantum states. So far, I feel like it's pretty intuitive that, how we're defining these structures. So now we get into the last two of our PUQCA, which is the tilings and the unitaries that we apply to these tilings. So we have three operators here coming from the quantum walk. So it would only be natural that we define three different tilings. So the three tilings that we define are, first is T0, which is concerned with the subcells within a single cell. Then we have these T1 IJs, which are concerned with subcells across different cells. And then you'll notice that T2 and T0 look the same. And the reason for that is, remember that when we apply the swap operator, we're still concerned with the same cells within a single cell. But if we're starting at I, we would have moved to another vertex at that point if we're considering the quantum walk case. We've moved to another vertex, so we're considering a different cell in this case. So the tilings look the same, but if we were considering a single cell, the cell that we consider for the tiling in T0 is different from a given cell that we consider for the tiling for a given tile T2. So there's not so a given tile in T0 would not be the same tile in T2 for the T2 tiling. I hope that wasn't confusing. Do you guys have any questions on how the tiling is defined there? No, okay. So as I was saying before, we have these tilings, and then by definition, we define some set of unitaries on these tilings. So this unitary should do, how the coin operators, the flip-flop, and the permutations were defined before. And then that's exactly how we define them. So our W0 then becomes our coin operator, which is related to the CIs from before. Our W1 then becomes our flip-flop tiling. And then our W2 becomes a permutation on the graph neighborhood, or on the neighborhood scheme for a particular vertex I. So I know we're running a little over time. Okay, so recall that we have our one-dimensional example for our coin quantum walk, and now we want to try and translate this over to a PUQCA. So let's gather the ingredients. So each vertex I becomes a cellular automata cell with two subcells each. So we have I, and then we define a neighborhood, or we have the left and the right cell, subcells. And then, as we defined before, we consider a translation from the coined quantum walk states to the cellular automata states. And then we do the same, we do that across both subcells within a cell. And then we have our coin operator, which is just a 2x2 unitary operator. And then we have our SX, which is just our shift operator. And the way we're defining that is that, you know, we're maintaining the direction and then updating the particular vertex that we're concerned with.
Yeah, I just want to add real quick. So the Sx here is going to be achieved by x times Si, x times the flip-flop.
So before we had the equation x times Si times C, so we're just condensing that here. So Sx is just, as Victor said, x times Si. So if we were to run through all the states, we start with this initial general state for the automata. Then after we apply W0, we see that this is the application of the coin operator. So we're updating that particular state as in that way, so that now instead of being all one, all one state is excited or all the other, now we have some sort of probability distribution for a given cell that we're interested in. Then we apply W1 following W0, and also remember that we're applying these W0s to every cell in our lattice. Then we apply W1, which is our flip-flop operator. And as you can see now, we've moved over into different subcells. So that's how we're representing the flip-flop. And then we compute W2 following W1, which is our shift operator. So then we permute the neighborhood, and then it flips basically. So yeah, and yeah, we can then, as we said before, we consider the evolution of all the automaton states using this this evolution function, where we apply W0 to all the tilings, all the tilings or all the tiles in the first tiling, and so on and so forth for the remainder of the two unitaries. And then we can also, I found this kind of interesting, you can define recurrence relations for the way this evolution is determined. I won't go into that too much.
Yeah, so
basically, I guess, yeah, sorry, go ahead.
No, I was just gonna add that essentially, if you follow this mapping from the quantum random walk to the quantum cellular automata, you're gonna get the identical state transition, the recurrence relationship. So it's gonna be so you successfully mapped a random walk, a coin random walk to a cellular automata. The transition recurrence relationship turns out to be the same if you commit to this kind of mapping.
Right. Yeah. That's what they were using to check the sameness. And then I think one thing that Victor and I were unsure about is sort of the results that they concluded in terms of the resources they used. So they were saying something like, okay, if we have V vertices in our graph, then we end up with V cells, and then each of these recall each of these cells has each of these cells has D subcells, and for each of these subcells, we say that each of these subcells is defined by a qubit. So then we would be led to believe that, okay, then in total for a given cell, we should have 2 to the D, that the 2 to the D resources are taken up. And then across all V cells, we would have V times 2 to the D. But somehow they're saying that's we have these single excitation states. So as you saw that when we initialize these states for each of the subcells in the cellular automata, we have this single excited state. Like everything else is 0 except for this one particular subcell within this particular cell. And what they're saying is that we can sort of disregard the resources that are taken up by all the zeros, and we can just consider this single excitation state. So they're somehow reducing the resources from V times 2 to the D to V times D, which doesn't really make sense, because if you're constructing a qubit, with this given, with this given dimensionality, it's going to have to stay that dimensionality. There's no way that you can treat those zeros as garbage, because you're going to have to use that in the calculation. So I found it kind of interesting that they came to that conclusion. Maybe, their whole thing was trying to address the drawbacks from before, that the walking space is too big and, the resources are too large, but it seemed like they took a little bit of a shady shortcut to convince the reader that, no, this is just as resourceful as a quantum walk. But I guess aside from that little point, basically what they're saying is that, the possibilities remain largely unexplored since cellular automatas are pretty recent. So like Richard Feynman, he sort of first proposed this idea that we should be doing computation quantum mechanically. And the whole idea of cellular automatas, and then after that, quantum cellular automatas came much later. So there's a relatively recent field, and the authors are saying that it should, receive more attention than it does. And they're positing that it could possibly serve as a catalyst, as a new way of describing quantum systems, as well as defining and developing effective quantum algorithms. They've already found, sort of as we're describing in this scenario, ways to do efficient search on these types of problems. So if you're to take a quantum walk, quantum walks have also been shown to be applicable in terms in quantum search type problems. So if you have a graph and you have a certain marked vertex on this graph, and you're a walker that's on some other vertex, and you're trying to find out where this marked thing is, then you can use a quantum walk as a way of finding out what this, where this thing is or what it is. So then you can translate that, as this paper shows, into a cellular automata and get the same results. So they're basically saying that we can use this structure as a way to define new quantum algorithms as well. And that's pretty much all the paper had to say. So yeah.
Thank you for the talk.
Yeah.
Although I still kind of wonder how they will actually apply that into a search algorithm, because wouldn't that basically simulate all the possible states and just choose one from it? And how's that?
Oh, with the dimensionality thing?
Yeah, I was just, because you said if there is one vertex that you're looking for and then you do the random walks thing, like eventually the random walks, the result will just be, the state will just be a superposition of all the possible states, right?
I don't really get how they're doing that.
Yeah.
But like, I guess the intuition would be, like the graph would have to be, like they would need to find a way to update a graph's probability distribution so that it would naturally gear towards that. But it's unclear on how are they going to do that for each query. Yeah, because like I guess intuition is that Grover search is essentially keeping that the superposition, but doing like angles, twitches, so that the some of the phase are amplified, and eventually the amplitude for the desired target is maximized, right? So I guess the intuition is that if you're a random walk, if your target is toward the right, then the probability of the edge going towards the right should be like maybe like 0.9 or something. But it seems like you're changing the graph structure for each of the query, so I'm not sure how that's going to work. But it could be like maybe we can just do that for next reading group. Would that be interesting? Like how quantum random walk is going to help us search?
Yeah, I think the main guide for that, based on what I've seen, is this guy named Zegedy. It's like Szegedy. I can send a paper that's like a lot of stuff that talks about quantum walks refers to this guy's one paper from
could you
2004.
Yeah, but I guess the biggest takeaway of this this paper is essentially that although the space requirement, the qubit requirement might even be exponentially worse, but the global unitary thing, I do believe that they have a point that we can really use global unitary. We can only use global unitaries for random walk, which is going to be quite large. It doesn't work.
It doesn't work. I put the snake all the way. It's something else. So we need to let me talk to the supervisor.
Okay.
What is the process? Because I think they need to call the plumber vendors or something like that.
Okay.
It's a big major thing.
Yeah.
I don't know.
Sure. Thank you.
Okay. Let me talk to him, and I'm gonna talk to you.
Cool. So there goes my garbage disposal system. And
you better cut this off from the recording.
Oh yeah.
I'm still recording. Anyways, so yeah, so the reason that random walk can only use a large global unitary is because they're essentially using direct sum, right? And that kind of blocks us from using a gate-based quantum computer because just think about it. Like we never know how to encode a superposition using direct sums, right? The superposition is always a tensor products, and when you're applying the gate-based model, however many inputs you're going to be putting, they're already tensor product, right? You can't use that for a direct sum of qubits. Does that make sense?
Right.
So that's why it's not easily encoded for a quantum random walk, but it is easily encoded for a quantum cellular automata because all of the states of the qubits, all of the operators are tensor multiplied, so they can be applied to each qubit in parallel. While a direct sum, you can't do that because there's no way you're going to decompose that and apply to a superposition of qubits individually, because it's a direct sum, and your input is a tensor product. It doesn't work like that.
Yeah, exactly. Because then the dimensionalities would be often
right.
Okay, I think this.
Although, as Samuel said earlier, something like the resource you need was pretty big, since one cell you need 4 qubits.
Yeah.
And
so I guess what they're arguing is that it's not that hard in the near future to get more qubits, but it is like fundamentally hard to like implement a gate that's going to act on all of them.
Right.
Makes sense.
Yeah. Okay, let's stop recording.